It's recording. Excellent. All right, so here we go. Got a little problem. It's a big problem, but we're recording it for you so you can watch as many times as you want. The concept is this. I have two different bases for the same space. In this case, the space is R3. So I've got two different bases for R3. Check them out. Not very nice bases. Now here's the deal. I would like to take a vector written in terms of one basis and write it in terms of the other. Let me show you what I mean. There is a vector over here that I'm going to be using later. You can see it up here. If I take one of the first vector in T, that's the 633, plus 2 of the second vector in the basis of T, plus 3 times the third vector in the basis of T, I get 29, 16, 15. This is a vector in regular old R3 space, but its coordinates in T basis are simply 1, 2, 3. That's the coordinates of this vector in T space is 1, 2, 3. In this space, the coordinates are 29, 16, 15. So this space is different from this space, but it's the same location. I'd like to find the numbers that give me the same vector here, but in terms of S. And here's how you find it. It's actually not tough. Here's what you do. You take a matrix made from the vectors. Let me just get them all on screen at the same time. The basis vectors. You see the S basis, okay, the T basis, and you row reduce the first one. Row reduce the first 3 by 3. When you get this to be an identity, this matrix takes vectors in T and gives you coefficients in S. Let's see it at work. So here's the matrix. Let me get that all on screen for you. A little more. All right, we got it. So this is my transition matrix. It's this guy right there. I'm multiplying it by 1, 2, 3. Remember, those were the T coefficients for the basis. When I do this multiplication, I get 9, 5, 6. These should be the coefficients in, it takes something in T and gives it to me in S. So 9, 5, 6 should work with the S vectors. I'm going to do the first one for you. 9 times S sub 1, that's this 9, plus 5 times S sub 2, plus 6 times S sub 3. Now if you look at the vectors, way over there, they're off screen. We have to pull back a little bit here. Let's see if we got them now. It's 9 times 2 plus 5 times 1 plus 6 times 1. It gives me 29, just like I was supposed to get. The other two calculations, 9 times the second coordinate, 5 times the second coordinate, 6 times the second coordinate, guaranteed gives me 16. Same with the third coordinates. So those are the coefficients, 9, 5, and 6. These three guys are the coefficients of this vector in terms of the S basis. So those numbers, I'm going to write them up in those little boxes for you. Those numbers in those little boxes are just a 9, a 5, and a 6. So I can write this vector or any vector in terms of both bases. And that's because suppose I had been given, instead of this thing in T, suppose I've been given it in S. So these are coefficients in S. Well, then I multiply by the inverse matrix. The matrix that takes S to T is the inverse of the matrix that takes T to S. And that should make sense, because the matrix takes T to S. Well, who undoes it? Who would do it backwards? Oh, the inverse matrix. Sure. So that's nice to know. And then the other big concept of the day is way over here on the right, and it's this. Basically, all the vector spaces that are three-dimensional. This is R3. The span of this is R3. The span of this is R3. The span of these three is R3. But it might as well be some other three-dimensional vector space, like P sub 2, polynomials of degree 2. Because you could treat 1, 0, 0 in R3 as 1 in P sub 2. You could treat 0, 1, 0 the same as x. you can treat 0, 0, 1 the same as x squared. All the stuff that you say about vectors in R3 are going to work for vectors in P2. Because those two spaces are isomorphic, and this is the isomorphism. That's the rule that shows you how these two spaces are different. Isomorphic is a fancy word for saying they're basically the same shape. It's the same space. It's just the names have been changed. The way we write vectors is different. But the function of the vectors and combinations, same stuff. So that's what's going on as we end chapter 4.